People still remember you. No problem.
Okay. So today I will present optimal nudging and also some comparisons between nudging, optimal nudging, and 4D VAR, hybrid schemes between nudging and ensemble Kalman filters, and so on. So yesterday I explained you that nudging is a very simple data assimilation scheme, and we will see that it's possible to make it very complicated using the adjoint. And then some comparisons on hybrid schemes with Kalman filters and 4D VAR. So just remember the problem. You have a model, you have some observations, and you would like to find the best possible state in blue. So the best possible will be for nudging schemes as close as possible to the observations. So just one slide to remember the standard nudging. The model equation is simply dx over dt equal f of x. So it can be almost anything. Here it could be a partial derivative, and here you have the spatial operators with some initial condition. And you assume that you have some observations of the system, y-ups, and you need some observation operator h to compare the observation and the model state x. So the standard nudging is simply to add a feedback term to the observations directly inside the model equation. And k is the nudging matrix. So how to choose k? That's the point, because it's the only parameter of the scheme. So the idea of optimal nudging is to use a variational data assimilation scheme to optimize k. So we will use the standard parameter estimation to determine the best possible matrix k, because we can assume that this is a model equation and k is a parameter of this equation. So we will use the 4D VAR cost function. So the standard 4D VAR cost function is there. There is the quadratic distance to the background state, xb. So it's an a priori estimation of the initial condition. B is the covariance matrix of the background error. And then there is the quadratic distance to the observations with the corresponding covariance matrix of observation error. So I think that you have seen that before. So it's the same within one slide. So you have the background here, you have some observations, and for a given initial condition x naught, first you compare x naught with xb here, and then you plot the solution of the model from x naught, and you compute all this quadratic distance from the observations to the model state. So here, okay, I just removed the background part of the cost function because otherwise it would, the equation would finish here. There is no problem with the derivative of the cost function for this term. So I just consider the observation part, and we can add, now we try to control also k, which is unknown, and we control it with this quadratic term. So k hat is an estimated nudging coefficient. It's like the control of the initial condition. So it's the same. You just control k is now an unknown, and you have to control it in order to ensure that the cost function is quadratic and strongly convex. So you need, usually if you want to minimize j, you need to add a regularization term. So you assume that you have an estimation, a priori estimation of k, which could be the identity matrix or H transpose. And you assume that you have some covariance matrix corresponding to this error. So if you don't know anything, you can just put H transpose, for instance, and here something simply a coefficient to have a good weight between the observations and the imaging term. So it's exactly like the background term. Okay. Yeah, it could be. We will see that it can be. So from the mathematical point of view, you can remove this term, but then the minimization of the cost function will be very difficult, because if the model is nonlinear, then the cost function is non-quadratic. You may have many local minima. So with this term, you can ensure that the cost function is strictly or even strongly convex, and then you may get the uniqueness of the minimum. Here, it's a it's implicit, because x is an implicit function of x naught and k. X is the solution of this model here. Okay. So for a given x naught and k, you solve this equation, and then you get x. Well, yes, you need probably to have something large enough here. Yes. But then probably for the standard for DARP, the cost function is never convex. So it will be probably the same here. So if you minimize j with respect to x naught, you find the best possible initial condition. And if you minimize with respect to k, you would find the optimal nudging coefficient. So how to minimize j? Well, you need the gradient of j. So the standard way to introduce the adjoint is to use the Lagrangian. So there is you want to minimize this cost function under the constraint that x, which appears in j, is a solution of the model equation with the nudging term. So the constraint is there. dx over dt minus f of x minus the nudging term has to be equal to 0. So you introduce the Lagrange multiplier p, integrate over time, and then this is the Lagrangian. So I just replace j by its definition, and here's the Lagrangian. Okay, so p, the Lagrange multiplier, is a function of time, because the constraint is a function of time. And now there is no more constraint, so x could be anything, p could be anything, k and x naught could be anything. So the idea is that minimizing j under the constraint that x is a model solution is equivalent to minimizing the maximum over p of the Lagrangian. Okay? There are two cases. So either x is a solution of the model equation of nudging, and then this is equal to 0, whatever p is. So the maximum over p is simply j. or x is not a solution of the model equation, then this is not equal to 0, and then the maximum over all possible functions p will be the infinity. Okay. So if x is a solution of the model equation, then L is simply J. If x is not a solution, then the maximum here is plus infinity. Then if you minimize a function that is either J or plus infinity, the minimum is simply the minimum restricted to this case when x is a solution. Okay, so minimizing something that is equal either to J or plus infinity is simply the minimum of J under the constraint that x is a model solution. So we are looking at for a saddle point of the Lagrangian. So all partial derivatives of L should be equal to 0, and we will compute all these derivatives. So the first one, which is the easiest one, is you want L to be you want a maximum on P. So the partial derivative of L with respect to P should be equal to 0. If you look at L, the only P is there, and the derivative is simply this term. So if the derivative is equal to 0, it means that x has to be a solution of the model equation with nudging. Then the minimum with respect to x. So we use an integration by parts because there was a dx over dt. So we simply replace p dot dx over dt by dp over dt dot x with the minus and the boundary terms. And then if you want that the derivative of this expression with respect to x is equal to 0, it implies that at any time, so the derivative of this term, we have done it yesterday, is if h is a nonlinear function, then you have to take the derivative h prime transpose r minus 1 times the innovation vector. Here you have minus dp over dt. Here you have the transpose of the derivative of x times p. And here you have also the transpose of the derivative of h times the transpose of k times p. So here is the adjoint model. And with this term, you also need that p of t is equal to 0. So this is the adjoint model that has to be solved backwards in time from the final condition. Okay, so the only difference with the standard adjoint of the 4-divar is this term here. Okay, there is an additional term, which is also linear in P. So now the minimum on x naught is standard. I just get back to this expression, and x naught is there only, so the derivative of L is minus P of 0. It's the same, nothing changed in comparison with the standard 4-divar. And the optimality condition would be that the adjoint state at time 0 is equal to 0. Then the minimum with respect to k. It's pretty easy to compute, except that k could be a matrix. So if you take the derivative dl over dk in the direction delta k, then it's simply the integral of g minus 1 k minus k hat dot delta k. So this could be a scalar product on matrices. Okay, some scalar product of matrices. And you have also this term here coming from the nudging term, k observations minus x. And this should be equal to 0 for all directions of differentiation. So for all matrices delta k. So the optimality system is there. So x should be a solution of the model equation with the nudging term and with the initial condition x naught. Then p is the adjoint model. Final condition p of t equal to 0. So backward equation in time. The standard model term, the standard forcing from the observations, and the new term coming from the nudging term. And then the gradient of j is there. Here it's the partial derivative on x naught. So p of 0 should be equal to 0. And the partial derivative on k is there. So the algorithm is similar to the 4D for a given initial condition x naught and a given nudging matrix k. You can solve the direct model with the nudging and then get x of t, all the solution x at any time t. Then you have to linearize the model and the observation operators around the trajectory x to compute the f prime of x and h prime of x. And then you can solve the adjoint model and get p at any time. Then you can compute the gradient of the cost function as a function of p. So here it's the gradient on the derivative on x naught and on k here. And if you have the cost function and the gradient of the cost function, you can update and get the new estimations of the controls x naught and k. And you iterate until you find a solution, or until you don't have any more time, or until the minimization gets stuck in a local minima. So the main problem is that you need a 4D var to do it. So it's very expensive, both the human cost to compute the adjoint and the computational cost to minimize the cost function may be very high because k is a matrix. So you minimize the cost function on a space of very large dimension. So you may need a lot of a large number of iterations to converge to a reasonable solution. Once you have optimized J, you have the best possible nudging matrix K, K star. And you may assume that this gain matrix may be used still as some optimal nudging matrix for the next time windows. Okay. The idea is not to optimize K on all assimilation windows, because it would be extremely probably the optimization of K, the computational cost is larger than simply doing a 4D var. So, and then you have to do some nudging scheme after. So the idea is to optimize K only once, and then you can update it a few weeks after. Okay, so let's see the link between optimal nudging and Kalman filter. So Kalman filter is the well-known extension of the optimal interpolation, or BLUE, to dynamical systems. So it's mainly you repeat prediction and correction steps. So you assume that you have some forecast, some estimation of your state at this time step, and you have some observation here. So you make an analysis. So you update the forecast with the difference between the observation and the forecast and the Kalman gain matrix. So you get an analysis, and then you use the model to compute the forecast at time k-1. And then you have a new observation. You can update the forecast and you have the analysis, and so on. So the same thing with equations. So you assume that you have the analyzed state at time tn, which is xan. You have some model operator. So here I assume that the model is linear, but it could be nonlinear. So the model here is the system resolvent from time tn to tn plus 1. And from the model, you get the forecast at time tn plus 1. You also need to compute the covariance matrix for the forecast error. So you simply, so it's the covariance matrix of the difference between the forecast and the true state. And you assume that you know the covariance error of the analysis state. So simply so if you assume that there is some model error, so here you should add epsilon, then the covariance matrix of the forecast is the covariance matrix of the analysis times the linearized model on the left and the adjoint model on the right, plus the covariance matrix for the model error. So this matrix is usually unknown. We will see that nudging could be useful to have a background estimation of this matrix. Then you have the analysis step. So the forecast is updated with the difference between the observation and the forecast using a gain matrix. And the gain matrix is the optimal matrix that makes the lowest possible error on the analysis. So you have to optimize, minimize, in some sense, the covariance matrix of the analysis here, and you find the best possible matrix, which is the Kalman matrix here. And then you can update with this Kalman matrix the forecast state, and you can also compute the new covariance matrix of analysis error. So then you simply iterate, compute the Kalman gain matrix, update the forecast to get the analysis, update the covariance matrix of the forecast to get the covariance matrix of the analysis, and then make the forecast, use the model from time tn to tn plus 1, and update the covariance matrix. So let's compare nudging and Kalman. So there are two main problems in the Kalman filter that I showed before. First, the computational cost of computing the error covariance matrices. So this is a well-known issue of the Kalman filter. And also the fact that you have to assume that all the covariance matrices are known. For the observations, it's almost true. Well, you can assume that this one is not very well known, but then the Kalman filter is known to correct the covariance matrix, and then after some time it should be good. But this one is probably never known. I think it's far from being known, because you don't know what is your model error. So if we try to write the nudging scheme like the Kalman filter. From the state at time tn minus 1, you get to the time tn by applying the model F, so here matrix M, and you add the nudging term here. Okay? So you can do it in two steps. You can first solve the model, dx over dt equal f of x, and then add the nudging term. Update your state with the nudging term. We have seen that the optimal nudging coefficients are obtained by minimizing this kind of cost function. So here it's written in discrete time steps. So simply take the quadratic distance between your state, nudging state, and the observation. So there should be some h here with the matrix G, which is the same weight matrix as before. So Kalman filter is the optimal merging of observation and forecast information at each time you have some observation. Okay, you use the optimal gain matrix, which leads to the optimal interpolation between the observation and the state. In the optimal nudging, the goal is to minimize the total difference between the observation and the analyzed state. Okay? The optimal gain matrix is the one that minimizes the difference over all the assimilation window. For a given nudging matrix, you compute the nudging state and you compare it with the observations. And you want to optimize it in a global way, like in a 4D VAR. Whereas in the Kalman filter, you do it at all the observation time steps. Okay? Each time you have some observation, you compute a new optimal matrix Kn, which is the Kalman matrix, at that time. Optimal nudging, you use the same matrix over all the assimilation window. So it's not the same. Okay, so in Kalman filter, the gain matrix is determined sequentially at each time step, well, at each observation time. And in the optimal nudging, you use the same nudging coefficients at every time step, and you determine the optimal coefficients in a variational way for all the assimilation window. So if you assume that you have the optimal nudging matrix, the computational cost of the optimal nudging is the same as the standard nudging. So it's very low compared to the Kalman filter. And you do not need any knowledge about the noise covariance matrix of the model error. Yeah.
Do you still require that the perturbations be small enough for linear approximations? In Kalman filter?
No,
in the nudging.
Well, here you can do it in a nonlinear way. I just wrote here in a linear way to compare with Kalman filter, but you can use the here it's completely nonlinear. So you just need to linearize for the adjoint model, but it's standard to get the optimal nudging. Once you have the optimal K, here you solve something which is completely nonlinear. Okay, the model is nonlinear, the observation operator is nonlinear, and this term is in some sense the model error, because you just modified your model in a way that you just add an additional term to the model in a way such that the solution of your new model is closer to the observations that if you don't add this term. So there is no need for the matrix Q, the noise covariance matrix for the model error, because now you have corrected your model in the best possible way. So for DIVR, so you can see the difference on this slide. The 4DIVR, you try to find a new initial condition to have the best possible state, the solution which is close to the observations. Whereas in nudging, you you start from the same initial condition and you correct the model and try to get the solution converged towards the observations. So if we are back to the 4DIVR formulation, there is a nice paper of Vidar, Ledimet, and Piacentini in 2003. I think it was in TELUS. So the idea is that they study the fact that the nudging term provides a correction of the model. The good point of the nudging, as we have seen yesterday, is that you don't assume the model to be perfect. It's a weak constraint data assimilation. So if you use the weak constraint for DIVR, you have to add the model error as a control of the cost function, and you assume that your model now is dx over dt f of x plus eta, the model error. So in the weak constraint for DIVR, you have to still control the initial condition. So here it's delta x naught is x naught minus xb, the background. You still have to be close to the observations, and you also have to control the model error with the covariance error matrix. So the idea is that it's well known that solving the weak constraint for DIVR is difficult. It's very expensive, and it's very difficult to give a physical interpretation of eta. Once you have your model correction, it's difficult to know what kind of physical terms you should add to your model to get a better model. So the idea is to simply use this model error term, which is a nudging term, k times the difference between the observation and the model state. And in this case, the minimization is much simpler. So, as before, you optimize or you minimize the cost function with respect to both the initial condition and the nudging matrix. So it's like the 4DIVR, but the optimization is harder because you have more unknowns. And it could be very difficult to optimize J if you consider all matrices K, typically full rank matrix. The dimension of K is it's a rectangular matrix, so you have on one side the number of grid points, so it could be 1 billion for instance, and on the other side you have the number of observations, which is a few millions. So the matrix could have nearly several millions of billions of coefficients. And if you want to minimize J, you have to identify all these coefficients. So if you remember that usually the minimization of a function in dimension n would require something like n iterations. You can imagine the number of years or centuries to minimize J once. So even if it's much cheaper than the weak constraint for DIVR, because in the weak constraint for DIVR you have to add this eta, which has the same dimension as x, but which is also a function of time, because your model error is a function of time. So it's even worse. Even if it's cheaper, it's a simpler and faster solution is to assume that K is not a full rank matrix, but either simply a scalar coefficient or a pseudo-diagonal matrix. So either it's a scalar coefficient and then you can assume that it's a function of time, because only one parameter may not be enough, or a pseudo-diagonal matrix, which means that the corrections are done only at the location of the observations. So there was a first comparison between standard nudging, optimal nudging, and variational data assimilation in a paper of Lodimé and Neven in '92. The tests were made on the National Meteorological Center model with 18 vertical layers. So there are several runs. First, you have the true solution. So you have some state. So the assimilation window is between here and here. So you assume that you have your true solution, and then from here you can make the true prediction. Then you can start from the initial guess, which is not the true solution, and simply integrate the model over the assimilation window and then for prediction without data assimilation. Then you can use nudging. So during the assimilation window, from the background state, you update with the nudging terms, and then you make a prediction. So for a prediction, there is no more correction of the model because you have no more available observations. And then the variational, it's a kind of 4D var. You minimize this with the model and adjoint, try to identify the new initial condition, which is the best possible initial condition, and then from this initial condition, you use the model to run, get the prediction. So here is the root mean square difference between the true solution and the identified solutions with the vertical layers here. So it's the divergence field, and it's for a 6-hour assimilation window. So the control is there. So here you have no assimilation. Okay. Then here you have the nudging, standard nudging. So you didn't optimize K. 12 hours. So the control is still there. You can see that the standard nudging gives quite bad results, probably because the estimation of K was not very good. The 4D var is there, and the optimized nudging is there. So I should mention that they did that without observation error. So that's why you get the best possible solution. You are close to the observations, which are exactly on the true state solution. We took some priori estimation, which is more or less simply the transpose of the observation operator with some coefficient, but they didn't tune. So there is no tuning for the standard nudging here. So just to show that even if nudging is simple, if you don't choose tune a little bit the nudging matrix, it can. Yes, but it's a nonlinear model, so if and the observations are discrete in time and space, so if you nudge too much, for instance, at the observation locations, you will get some shock in the model solution, then you may have some gravity waves, so it could be very bad. And so they also showed that if you increase the length of the assimilation window, then nudging becomes more and more efficient because it's you have the asymptotic convergence in time. So you need long time windows to get something very good with nudging. So in this paper of TELUS 2003, they used 1D Burger's equation, which is a very simple model. It's a very nice model from a mathematical point of view, and there is it's a very, very, very simple model for atmospheric circulation, also to study some wave equations. So you assume that you have some discrete observations, and then you can add this nudging term here at the time of the observations and at the location of the observations. So there is no smoothing here at the moment. And they assume that as you are in 1D, you can optimize the nudging k at all the time, all the observation times. So they considered several gain matrices. So either full rank matrix at all the times. So it means that at each point of the grid model, you will correct your solution with a linear combination of all your forecast state and observations available at that time. Or you can use a pseudo-diagonal matrix, which means that you correct only at the observation locations. But then it's also a function of time, so the correction coefficient is different for each observation. Or you can assume that it's simply a scalar coefficient, so it's the same correction coefficient for all the available observations at a given time. So it's just a function of time. So they also considered a smooth version of this, because this could be very bad if you simply correct at one point. Then you get something which is the solution is not physical, and then the model may have bad behavior in the few time steps after. So you can add a linear time interpolation. So simply, as I showed yesterday, so here is your time of observation, and you add some, for instance, like this, over several time steps. So the correction is not only at this time, but also you make a small corrections, 1 or 2 time steps before and after. And also temporal smoothing, so usually it's a convolution with a Gaussian kernel, so that on your grid, you don't correct only at the location of the observation, but also on a small neighborhood of this point. So in this case, you are almost sure that the correction will be quite smooth in time and space, and then it will be more or less consistent with the other grid points, and then there should not be any gravity waves in the model. Okay, but because if you assume that you have a solution like that, for instance in 1D, and then at this point you make a correction, and you put this point here, so now your solution is like that. So if you run the Burger's equation with this kind of solution, you will get very quickly some wave, and probably if the diffusion coefficient is too small, you will have a shock, and then the model will you will get an explosion of the solution. So it's not good. So here's the result when they optimized. So they compared with no assimilation, a 4D VAR, and then with 3 optimizations of the nudging matrix with either a full matrix, a diagonal matrix, or a scalar coefficient. So you can see the size of the thing that is optimized is the size of the control vector, which is minimized in the 4D VAR, and is the number of observation times. So it's the most simple nudging matrix when you take only a scalar coefficient at all, which varies in time. If you use a pseudo-diagonal matrix that at each observation time you also have to optimize the coefficient for each observation, if you have many observations at a given time. And if you take the full matrix, then you have to multiply by the size of the control vector. So 4D VAR is quite fast because there is no model error, just you optimize the initial condition. It's a 1D model, so it's very fast. And then the optimization of the nudging coefficient. If you take a scalar coefficient or a pseudo-diagonal matrix, it's almost the same time, computation time as the 4D VAR. But if you want to get a full matrix optimization, then you increase a lot the size of the control vector, so you increase also the computation time. But you get a best solution. The root mean square error is smaller with the full matrix than with diagonal or scalar coefficients, and it's also better than the 4D VAR. And of course, it's much better than if you don't do any data assimilation. So here it's the same with the smoothing nudging. So the computation time is almost the same, but you can see that the root mean square error is much smaller because you avoid all the shocks in the model. So here you can see the evolution of the RMS error on the SSH. For the 4D VAR, the optimal nudging and the smooth optimal nudging. And so the windows were 3 days, and they performed the assimilation over several assimilation windows. So the 4D VAR is there. And what you can see in the standard nudging is that you get some, the assimilation window is there, and here you have the observation times. So you get the standard shape of the 4D VAR, which is the, even if you optimize the initial condition, usually the norm of the error is the minimum near the middle of the interval of the assimilation window. It's quite standard with the 4D VAR. The initial condition and the final condition are not as good as what you get in the middle of the assimilation window. So Talleyrand has an explanation of this, but I never understood it, so I cannot tell you. So what you can see with the standard nudging is that when you correct the model with the observation, you have some shocks and gravity waves, and then you need many time steps to get back to some kind of physical solution. So, to the true solution. No, to true solution.
When you actually initialize to make the forecast in 41, you use the minimum, you use the, or do you initialize at the 30 days?
I think that they made a previous computation before, and then they use the forecast they get, and then they start again with these solutions on the previous simulation window. Yeah.
Not at the 15 days.
They did some computation for the month before, and then they used these solutions to initialize there. Because if you can also have trouble if you initialize with something which is not a solution of, for instance, in nudging, if you start with a solution which is not a solution of the nudging model, then the first time you add some correction, you may have gravity waves and so on. And I think that they initialize with the previous result. So nudging is bad if you don't smooth the correction in time and space. This is the point. With the nudging, yes, because you correct, each time you have some observation, you correct the solution with the observation. So it's like in a Kalman filter. So it increases when there is no observation, and then when you make the correction, it decreases. So it's like... for nudging, because between two observations, you have no correction. It's only a forecast with the model. So at the beginning, it decreases because you... At the beginning, it decreases because the model is always, you first reduce the error along the stable modes, and then the unstable modes take some time to make the error increase. So it's the same as the Fordivar. Usually, for the Fordivar, it's standard because when you start with an initial condition which is not correct, then you have some error along the initial condition. And at the beginning, the first time steps, you have the stable modes of the model that stabilize the model, so the error decreases exponentially in time. And then after, you have the unstable modes with, if you imagine a matrix with positive and negative eigenvalues, when you apply the matrix to a vector, first the negative eigenvalues will make the error decrease exponentially in time, and then the positive eigenvalues will make the error increase exponentially in time, and then it will never stop. It should never stop. So it's always like that. It's always first the stable modes make the error decrease, and then the unstable modes make the error increase. Yeah, it's a continuous run. And for nudging, it's the same. At the beginning, it decreases, and then after it increases. But then, like in Kalman filters, when you make a correction with the observation, you have a step, and the error decreases. But it's a 30-day forecast. Well, here it's not a forecast; it's the assimilation window. Okay, the forecast would be there. So the idea is that if you smooth the correction, first, if you optimize nudging, you get something probably similar to Fordivar. And then if you smooth the corrections, you have something better and smoother, and you have no gravity waves, and even if you have some oscillations, because you add, let's say, non-physical, well, a correction which is not coherent with the physical model, then you have some small oscillations, but it's not as bad as for the raw optimal nudging scheme. Okay, what you don't see maybe is that once you're there, for instance, there is a correction, and then the time step just after, you have the gravity wave. Okay, so you don't see, but it decreases first, like here, but then there is the gravity waves, and so you lose almost everything. So, a few slides on a hybrid scheme. So the idea is to improve the ensemble Kalman filter with nudging. So ensemble Kalman filter is some kind of Kalman filter, but you have an ensemble of states, and you run the Kalman filter for, you run your forecast for all the ensemble. And then when you compute the covariance matrix, you use the covariance matrix error of your ensemble. And then you update. Okay, so the background error covariances are computed from the ensemble forecast. And it's the same as the standard Kalman filter. You have an analysis and a forecast that you iterate. And like in Kalman filter, you have discontinuities at the observation times, because you add a correction like there. You have discontinuity, and you may have some trouble also at the observation times. So the idea is to improve that by applying more continuously in time the corrections. It's more or less like the incremental analysis update, IAU method. Maybe you have seen that. The idea is that once you have an analysis, then instead of correcting the state at one point, you get back in time and try to integrate over time this correction. So the idea is to use a nudging term to gradually apply the correction in time, so that you will not get some shocks in the solution. So the idea of the nudging is that in time you will have some smooth correction term. Okay, so the difference between the observation and the state vector. Then you add some function of time with this kind of shape. You can add also smoothing in space with the convolution with a Gaussian kernel and the nudging matrix. In the ensemble Kalman filter, it's like the Kalman filter itself. You correct the forecast with the observations and the Kalman matrix, but then there is some shock. So the idea is to add this correction coming from the ensemble Kalman filter, but in a smooth way in time. So not exactly at the observation time, but on a few time steps. So here is the idea. You have the ensemble states here, so you have many solutions. So you have 5 here, for instance, and you also have the nudging state. So you assume that the black here has been done, so you have all the forecasts of the ensemble. You have computed the ensemble Kalman gain matrix. Okay, so you have done the this step in the ensemble Kalman filter. And the gain matrix that you computed in the ensemble Kalman filter, you use it for the nudging matrix. Okay, you use this matrix, this particular matrix. If it was a standard Kalman filter, then once you have computed the Kalman gain matrix, you use it for the nudging. But you add the regularization in time and space, so that your nudging state is quite smoothly corrected. So you compute your nudging state here, by continuously applying the nudging term with the coefficients of the nudging matrix coming from the ensemble Kalman filter. Then, or you can do it in parallel, you update your ensemble. So from this prediction here, you make the analysis in black here. And then you shift the ensemble in a way that the mean of the ensemble is the nudging state. Okay, so you use the nudging state that was computed with the help of the Kalman gain matrix to shift from the black to the blue so that the mean of your ensemble is exactly the nudging state. You just shift, so and then you integrate in time to get the new ensemble forecast and the nudging state also. Okay, so the idea is that the ensemble Kalman filter gives the best, in some sense, best correction matrix. You use it for nudging. It gives a state which is probably better than what is given by the ensemble Kalman filter because you add the correction quite smoothly in time and space. And then you shift your ensemble to be centered at the nudging state. But you keep the ensemble and then you move to the next step.
So you could have let the whole ensemble go forward under the nudging system?
Probably it will change the distribution of the ensemble, which may not be a good thing. The idea is here only to change the mean of the ensemble, but not the spatial distribution. So Dave Schoeffer and his team, they tried this hybrid scheme on Lorentz model and then shallow water models, and they get better results than the ensemble Kalman filter and also than the ensemble Kalman smoother, even if in this paper they did the smoother with only one observation time for the correction backwards in time. So the idea is that this hybrid scheme gives gradual corrections of the state, and then you avoid the strong corrections and discontinuities in the solution, which is always a good point. So maybe I don't know if you have seen ensemble the Kalman smoother already or no. So the idea of the smoother is that when you apply Kalman filter analysis, then you have a step in the both in the error of your solution, but also in the solution itself. If you look at the solution and not only at the root mean square error, you will see that you can get some shocks, and you may have some waves in the few time steps after. So it's not good. So the idea of the Kalman smoother is to try to reduce this, and also try to use future observations and not only past observations. Okay, Kalman filter is a sequential data assimilation, so you only use the observation when you have a new observation, new available observation. The idea of the smoother is to use some observations that will be available in the future to correct the past state. So, so you assume that you have the forecast here, and you have some observation. You make the analysis like in a Kalman filter. Then you compute the forecast at the next time step. You have a new observation, so you compute the analysis. And from the knowledge of this observation and the forecast here, you know that the forecast is not very good because the observation is there, the forecast is there, and so you could correct the analysis there from the knowledge of this observation. And then the idea is to get a better analysis there, such that if you take the forecast, you will be closer to this analysis. Then from this analysis you compute the forecast, you have a new observation, compute the analysis, and here it's the same. From the knowledge of this observation and what you did, the interpretation you did here, you can correct the analysis here. Okay, the idea is that this analysis is the best interpolation between these two states. This one is the best between this one, but also this one, this one. And you can get back in time, use this to correct this analysis here. So you can do it for many time steps. You increase the computational cost, but then probably you will get something which is smoother in the corrections than simply doing the Kalman filter. So here's what they get for the 2D shallow water. So it's the RMS of the height, sea surface height. So at the beginning it's not very clear because the shallow water model is quite stable, so you can do almost anything. At the beginning everything is nice, but after some days you can see that if you don't do data assimilation, then you have a larger error, which is standard. The nudging is in blue, so it's better, and it can be better sometimes than the ensemble Kalman filter. The ensemble Kalman smoother is almost like the ensemble Kalman filter because they use only one time step correction. They didn't use 2 or 3 or 4, so the correction here is quite small. But they are publishing a paper in this year with much better results. And the point is that the hybrid ensemble Kalman filter in black is much better than the standard ensemble Kalman filter. Simply because there is no discontinuities in the solution, and then there is no oscillations or gravity waves in the time steps just after the correction, which degrade the solution. And for the wind field, it's different. So you can see that the standard error for the velocity in a shallow water model is usually very high, because in this kind of model the wind field is there is a huge current somewhere in the domain, and then elsewhere there is almost nothing. So if the current, for instance the jet stream is misplaced from a few grid points, then you have 1% error immediately. So if there is no data assimilation, the wind field is bad and remains bad. With the nudging, as they observe mainly the sea surface height, and they haven't done what I showed yesterday. They didn't correct the wind field from the height observations, so the reduction of the error is not very good at the beginning, but then you have some asymptotic convergence. The ensemble Kalman filter and smoothers are here. So I'm not sure what they did with the ensemble Kalman smoother, because there are some peaks here, but anyway. And what is good is that the hybrid ensemble Kalman filter nudging, at the beginning it's simply the nudging, and then here you have the corrections of the ensemble Kalman filter, and you can see that the black curve is, you get something smoother. There is no peak, no step here at the corrections, the observation times. So you get something smoother and better than the ensemble Kalman filter itself. Okay, so the conclusion is that optimal nudging is a very, very efficient data assimilation scheme, but it's very difficult to implement it because it's nudging plus 4D var. So probably if you have a 4D var, an operational 4D var, you would not take the time to add the nudging on it. Or probably if you prefer nudging, you will not take the time to add the 4D var. So you usually get similar or even better results than 4D var or Kalman filter, but the optimization of the coefficient, the nudging coefficient, is very, very expensive for the human cost and the computational cost. And the idea is that you can use the nudging for hybrid schemes, mainly with filters, Kalman filters or smoothers, because you can spread in time the corrections in order to get more smooth solutions and better solutions. So this is the idea of the nudging. This optimal nudging is, I think, no more used because people, if you have time to compute the full 4D var with the optimization of model parameters, then probably you stay with the 4D var. And so the idea is to use nudging to improve other data assimilation schemes. Okay, thank you. Questions?
So, yeah, in this last bit there, you hybridize the filters, but you didn't hybridize samples, right?
No.
You somehow got rid of the jumps by, so like the smoothers get rid of the jumps, your hybrid filter got rid of the jumps. So what's the intuition behind that? Why does that happen?
Why is the smoother?
Well, I can see why the smoother gets rid of the jumps,
Yeah.
but why does the hybrid filter get rid of the jumps?
Because you don't add the correction at exactly the observation time. You use a Gaussian or linear function in time to correct your state, not only at the time of the observation, but at the previous and the next time steps. So you have a smoother correction. It's gradually in time. So it's much better because you use the model. The model filters the correction over several time steps, whereas in the standard.
Sounds like that's a question of what you're plotting, right? Because you do the ensemble Kalman filter and then you shift the mean, right?
Yeah.
If you had plotted it rather than plotting the nudge state, you would have seen the shot.
Well, you can remove the ensemble and just do it with the Kalman filter. When you have your forecast and when you make the correction, there is a shock. Okay, there is a step in the error function, but there is a shock in the solution. Because you add something which is not a model solution. So your solution is slightly modified at one time step, and then the model will say, okay, what happens there when you compute the derivative in time? Because there is if you use, for instance, leapfrog schemes in time, you will see that the difference in your solution between two time steps will give also a difference with the next time step, and you will propagate this thing, and you can get gravity waves. With a shallow water model, it's very simple. You just add a correction a small correction at one time, at one grid point, at one time step on the sea surface height, and then you will see a gravity wave, a very fast wave on the few time steps after. So the idea of the nudging is that instead of doing, okay, let's take this, and then maybe with gravity waves, you are doing this. You spread the correction over several time steps, and then at each time step here you add a small correction for which the model is will not behave in a bad way. And then at the end you almost add the same thing but spread in time. So yes, this is the nudge state and this is the Kalman state. I don't know. Well, it's, yeah. The idea of this is almost the same as the incremental analysis update, is that once you have done your correction, then you get back to the beginning and you try to add your correction smoothly in time to arrive there, but without any shock. So the idea is almost the same. If you assume that there is, it's simply the Kalman filter, you compute the Kalman solution, you update the nudging state, and it's better to use the nudging state than the Kalman state. Okay, so because you do it like that instead of like that. So for the ensemble it's the same, but you have the ensemble, so instead of having one, you have many here, with the mean here, and then you just shift. Yes, probably it's the only thing that it does, because at the end I think that you almost have the same correction, but if you look at the solution itself, you don't see any spikes, or they are much smaller. Okay.
We are expecting the announcement. Nothing.